We are Team P21571, working on the Solar Radio Telescope 2.0 project for the 2020-2021 academic year. Our project focuses on the particles from the Sun's radio frequency emissions that can be harmful to power lines and Earth satellites and can cause billions of dollars worth of damage. These damaging particles take 2 to 3 days to get here, but the Sun radio waves get here in just 11 minutes. A solar radio telescope would function as a warning system to prevent these expensive losses by autonomously tracking the movement of the Sun throughout the day. Tracking the Sun's RF data will also collect more information on the Sun's processes and could create predictive models. The main goal of this project is the system integration of previous models and the addition of low noise amplifiers to look at the night sky. Also, we expect to have a user interface that would allow different types of users to interact with the SR telescope. For our approach, we first reviewed previous teams' progress and compiled all of the available documentation, since there were various versions of this SR telescope in the past. Then, we proceeded to test the current performance of the system handed to us. Where issues arose, we focused to solve any software or hardware issues from the previous iterations before integrating these systems together or implementing new features. Currently, we've finalized compiling information from previous teams, perform maintenance on the system's mount, and enable remote access to the main PC for everyone. In the following video, you will see the mechanical system in the mount moving. This would allow the satellite to automatically follow the Sun's trajectory during the day and capture accurate data. This graph is a proof of concept for the type of data we will be able to capture with the radio telescope. Here in the left, we can see the actual sunspots at the time of the test, and on the right, we have the setup used to capture the radio frequency signals. The red and green lines show the sun signal, which has already been processed to remove ambient noise, which is represented by the blue line. This breakdown of the signals is accomplished using a receiver in the dish facing the sun that captures the raw signal with the noise included. Then, using the dipole mounted at the back of the dish, we can capture only the noise, allowing us to mathematically distinguish the actual sun signal from the noise. In the plot, for example, notice how channel 8 in the 657.5 MHz frequency shows high signal strength in the blue line for noise, but no effect in the red or green lines. The difference between the red and green lines is that for the green one, we have the low noise amplifiers, LNAs, turned on, boosting the sun signal received.